Hello everyone, Gustavo here. Today I want to take a look at something super important, which is these ideas of transforming vectors. And one of the most important transformations that we have is rotation, right? You should be able to go and rotate a vector by a certain angle, right? Radians, degrees, we should rotate that vector by a certain amount. And if you open a mathematics book, or if you open a physics book, or even a computer graphics book, you will see that most books, they will give you these two formulas right here. Right? So the x prime and the y prime, x prime and y prime are the new components, x and y, of the rotated final vector. Right? So the new x component of that rotated vector comes from the original x of the vector times the cosine of that angle beta that I want to increase, right? I want to rotate by, minus the original y of the original vector times the sine of the angle beta that I want to rotate. This is how I find the new x component of my rotated final vector. And the y component, what I'm calling y prime, comes from the original x of the original vector times the sine of the angle beta plus the original y of the vector times the cosine of the angle beta. Most books will give you these formulas and they will say, look, just accept that this is true, let's move on and let's look at applications, right? What I want to do today is I want to pause and I want to look at these two formulas and I want to prove that these two formulas are true, and I want to prove and show where they come from, right? So let's try to give some intuition. Let's look at some geometrical problems, geometrical statements here to see where these things come from. And I think this is super important for us as programmers, especially because I just don't want you to go home and just accept that this is true. Let's try to understand why these two formulas are what they are. Let's just quickly reduce our problem and look at something simple. In our 2D vector rotation, right, what we want to get is, given that we have our Cartesian plane, right, we have x-axis, y-axis, and we have a certain vector position, right, we have a little vector that has the original components x and y. This is our original vector. Do you agree that that vector is already rotated by a certain angle, let's say alpha? So this is the original vector, and if we compare with the x-axis right here, it forms an angle alpha, right? This is the original angle of the original vector. What I really want to do is I want to get that vector and I want to transform. So I want to go and rotate that vector by a certain amount. I'm calling that amount beta. So I had the original alpha. I want to now rotate by an amount beta in angles. And this thing right here, right, this is our goal. Our goal is to find the new coordinates x and y of the point x prime and y prime after we rotate the vector by the beta, right, by that angle beta. Look at it again. This is the price that we want. We want to find the new coordinates of the rotated vector, right? So after we got that thing and we rotated, we want those components, x prime and y prime. But before we move forward, I just want to pause very quickly because I want to do a review of those important things, sine and cosine. Remember how we saw the sine, the cosine in the formula? So just very quick, right? 2-3 minutes, a Trigonometry 101, very quick review. So sine, cosine, and tangent. These are the three things that I'm going to very quickly touch, just so we are all on the same page when it comes to these things. Look, when we talk about trigonometry, right? Trigonometry is this field of mathematics that studies trigons, right? Trigons being these three-sided polygons, aka triangles, right? So trigonometry is the study of trigons, triangles. And whenever we speak about triangles, let's just look here at this example. I am just going to give a vanilla triangle here. I'm going to show a vanilla triangle here. This thing right here is what we call a right triangle, right? It forms an angle of 90 degrees right here. And let's say that given that we have this vanilla triangle, both in color and in shape, I have that angle right there, right? So it forms an angle in that side. You probably know that we call the sides of this triangle some funny names, right? And mathematicians, we love these funny names. So I want you to remember that whenever we have this triangle, and that is the angle that we are talking about, this side right here, which is the opposite side to that angle, we're going to call it the opposite side, right? No surprises. This thing right here, I am going to start calling this thing opposite side because it's opposite to that angle. And of course, the base right here, this side that is adjacent to the base of that angle, I'm going to call that the adjacent side. So we have the opposite side to the angle, we have the adjacent side to that angle, and we still have one side, which is the longest one, right? That one. You probably know that we call that thing a very funny name called hypotenuse. So from now on, I'm going to start talking about this lingo. I'm going to use these names: hypotenuse, opposite side, adjacent side. This is what I mean when I talk about these names, right? I'm pretty sure most of you remember this from your elementary school, high school, but so we're all on the same page. This is what I'm going to talk about. Because in the proof that I'm going to use, I'm going to start using these names: opposite, adjacent, hypotenuse, and they're going to mean something in the triangles that we're going to see in our proof. Right. Together with this thing right here, there is three important things that come, which we call trigonometric functions, but they are called sine, cosine, and tangent. But what I want to do is I want to simplify, and I want us to all understand intuitively what that means. So let's just start with the simple one. Whatever we call the sine of an angle, so if we are talking about the sine of that angle right there, the sine is nothing but the ratio between two things, right? I always wanted to think that the sine of an angle is a ratio. It is this fraction right here. It is something over something else. So the sine is this ratio between the opposite side divided by the hypotenuse of this right triangle. That's it, right? So the sine of an angle is a number, right? It's this ratio that tells us how much something grows, how much something shrinks, given that we have this ratio. So as the opposite side grows, what happens to the sine? If the hypotenuse grows, what happens to the side? It is a ratio. Always remember that. Right, so this is the sine, right? It is the ratio between the opposite and the hypotenuse. And we have something called the cosine, which is, probably no surprise, it is the ratio as well between now the adjacent side, the base, divided by the hypotenuse. So if I get the ratio, that fraction between the value of this side adjacent over the hypotenuse, I will get a number, which is my cosine of that angle alpha. Ratios, that's it. There is another important one of these functions, which we call the tangent of that angle, and the tangent is the ratio between the sides, right? The opposite side over the adjacent. So if I get the opposite side and I see the ratio between these two sides right here, the opposite and an adjacent, that is what we call the tangent, right? Look, I think most of you remember something called SOHCAHTOA, which is something that we tell kids to help them remember what is sine. Sine is the opposite over the hypotenuse, right? O over h. So the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So SOHCAHTOA might help us, right? If you want to use that, it's good. So sine, cosine, and tangent, this is what I wanted to remember for us to continue our proof, right? So let's move on right here, and let's go back to our problem statement, right? Now that we reviewed these things, what we need to find now is we have the original vector, x and y. I have this angle right here, which is the original angle that is formed with the x-axis. And do you see how I'm calling the distance between the origin to this vector? I'm calling it r. The reason I'm calling it r is because if we go and you rotate this vector around the origin, do you see how we can basically form this circle of rotation, right? This full rotation will form a circle, right? I have this circle around the origin. So since I have that circle, this distance, it kind of makes sense for me to call it the radius of that circle, right? So r because of this detail of the radius. Cool. So this is what we have so far: x-axis, the original vector, the original components x and y of my original vector. And if we break this thing apart, if I project here, this is the x and this is the y of my vector, right? So let's look at this. Given that we have this thing as the x of my vector, and given that we have this as the y, right? This y right here goes on the other side. Given that we have this configuration right here, do you see how we have this right triangle? It's almost like we have this right triangle here, right? Formed by the height of my vector, the base of my vector, and that angle alpha. We can see this thing as the adjacent. This thing is the opposite side. So we can come up with those cosine and sine formulas, right? So let's just think of what is the cosine and sine of the angle alpha here, given that we have this adjacent and this opposite side. Cosine of alpha is the adjacent, right? So it is cosθ, so cosine is the adjacent over the hypotenuse r, x over r. Makes sense, right? So this is one. The sine of the alpha will be the opposite of that triangle divided by the hypotenuse r, so y opposite divided by r. No surprises there. And I'm going to actually, what I'm really interested in is to find these values with respect to x and y. So with simple, if I want to find x, simple algebra here, right, just multiplying everything by r and sending r multiplied over there, x is r times the cosine of my original angle, and my y, again, is the r times the sine of my original angle. So, right, so simple algebra, just multiplying things. I think everyone got this. These are the two formulas that I'm going to use to help us in our proof very soon. So x is the r cosine of alpha, y is r sine of alpha. These are my original x and y values, right? The x and y components of my original not rotated vector, right? The vector that is before rotation. So these formulas are so important that I'm going to borrow them from here, and I'm going to get them from here, and I'm going to post it on the next slide. So I'm just going to put up there x equals r cosine of alpha, y equals r sine of alpha. Coming back to our problem here on the slides, this is what we have, right? We have the original vector with the components x and y, and then after we rotate, we're going to end up with this new x and new y, right? The x prime and y prime. This is what we want to find, right? We want to find the coordinates x prime and y prime after we rotate the vector. This is the whole point of this lecture, right? We want to find the x prime and y prime, the components of the rotated vector. So we also, right, I think it's no surprise that the distance from the origin to the vector is the radius, right? It's going to be that radius of the circle, rotation circle that we have. So I also think that it's easy to understand that if this thing right here is r, after I rotate by an amount, I still have r, right? The side, the distance between the origin and the vector is not going to change. So those things are true, right? This distance is equal to the other distance. I'm calling it r. Very well. And I also have the idea of my angles, right? So this was the original angle alpha. To find the new rotated, I'm going to rotate by this beta amount. So the new x prime and y prime components of that vector, I want to find this x and y after I rotate by alpha plus beta, right? This is what I want to find. This is the relationship that I have. Right, so now that we have all this information, I'm just laying down the problem so we have everything that we need to find the relationship between the values, right? And as soon as I have this thing, one thing that I'm going to do is I'm going to project everything. So I have all these lines that I'm projecting. So this is the x of this component here, this vector, that is the x of that vector, this is the y. So by just projecting things into the axis, we start to enter this geometry problem, right? And you probably notice that we have some useful information, right? This triangle that just happens to be formed right here, it is a right triangle. This thing right here is a right triangle. This is a right triangle. So there are several useful things that we're going to just borrow from geometry, right? We're going to use these Euclidean geometry axioms to help us come up with this relationship between values, see if something is equal to something else. That is how I'm going to approach this. Just so we make our lives a little bit easier, I'm going to give some labels to these important vertices of this problem. All these things, right? A, B, C, D, E, I just put some labels in these important intersections of our triangles and etc. So I have A, B, C, D, E, F, G, and H. We're going to use all these letters to understand what is going on with our proof. Very well. So we want to start. I'm going to start by analyzing a couple of things that we know are true. Right? So, for example, if we have that angle beta right there, right? So do you see beta? That is going to form this triangle right here. So A, B, and D is a right triangle. Knowing that we have a right triangle, I can understand that idea of the sine and cosine, so I can find out the opposite side over the adjacent. Let's see if we can find out the base of this triangle right here, AD. So do you see AD is the base of this triangle? I can find the cosine, right? So the cosine of my angle beta is AD, which is the base of this triangle, divided by the hypotenuse. And the hypotenuse is R, as we know. You see, if you need to pause and really make sure that what I'm telling is true and I'm not making any mistakes, you can pause and really make sure that you understand the whole interpretation, right? So AD divided by the hypotenuse will give me the cosine of that beta angle. And just again, simple algebra here, just multiplying R with cosine, AD, right? So this side, AD, the base, is equal to R cosine beta. This is going to be important for us, right? So AD is R cosine beta. And I also can find the sine, right? I can also find this value right here by using the sine of the angle beta. So the opposite side, BD, divided by the hypotenuse is the sine of my angle beta. All good so far? So I just multiply again R there, simple algebra. Now BD, this side right here, is equal to R sine beta, right? I just multiply R, this is it. These two things right here are important. I'm going to save them and I'm going to post them in the slides, right? So these two relationships right here, AD and BD, they come from these expressions, right? This is the equations that I'm going to use. I'm going to save this thing and put there, right? So I'm just saving them there. AD is that thing, BD is that value. Right, next step. So what I want to find out is this. Eyes on the prize, right? We want to find the x new component and the y new component of this rotated vector, right? This is what we want to find. So if we look at those components, what is the value of x and what is the value of y? If I look at the x component, right, just x is AE. See if you agree with me. The x of that rotated vector is that base there, A to E, right, from A to E. I can also look at x, right? If I really flex a little bit, I can look at x as AF, so the entire AF minus that subsection EF. So AF minus EF will give me the resulting AE that I want, which is the x. Right, so this is true, AF minus EF. Do you agree that EF, the base EF, is on that rectangle there, right? So the base EF is the same as CD. So the base of that rectangle EF is the same as the top of the rectangle CD. So I'm not going to use EF, I'm going to replace this EF by CD because they are the same, right? So CD. So what I did was, instead of using EF, I use CD, which is the top of the rectangle. Right, so we need to find AF and we need to find CD. Those are the two sides that I need to find to get the final x prime that I want. First things first, let's look at AF, right? Let's just focus only on this first term. AF. AF is the base of that triangle there. I can think of the base of that triangle as, well, the cosine of that angle alpha is going to be the adjacent AF, right? So it is the adjacent from A to F divided by the hypotenuse from A to D. So I have this relationship. The cosine of alpha is the adjacent over the hypotenuse AD. And I want us to pause for a moment and let's look at this expression here that we just found out. Do we have anything here that we already can replace that we know? Look at the denominator AD. We have the value of AD from before, right? We already have some information about that side AD. So I can basically replace this denominator right here by the r times cosine of beta. So that's what I'm going to do. So the cosine of alpha is my AF divided by r cosine of beta. What we really want to find is AF, right? This is our goal. We want to find AF. So AF, just multiplying everything by r cosine of beta, sending this thing multiplying, it is the cosine of alpha times r times the cosine of beta. And this is true. This is a great information, but there is something else that I can look here, right? So look at this thing right here. Look at this cosine alpha times r. What is cosine alpha times r? Look at the slide, right? Look at the blackboard here and see if you can find cosine of alpha times r. Yes, we have that, right? It is the original x. So cosine of alpha times r, it is x, r cosine of alpha. So we can just replace this thing by x, our original x of the original vector. That gives me this important thing right here. So AF is equal to x times the cosine of the angle beta. Very well. This is the first term here, right? This is AF. So we just found AF. We need to go now and look at this second term right here, right? Because we have this negative CD. So we need to look for CD. That is our goal now. You see how we are breaking the problem apart, looking at one thing first, the other thing next, and then we're probably going to join these things at the end and find the final result that we want. So let's look at CD. Well, CD is the base of that triangle right there. If we pause right now and if we look at this problem as we have, I don't think we have enough information yet to solve this CD. Looking at it, I think it would be useful for us to know something about this triangle here at the top. Do you see the triangle BCD? I think we should probably try to solve and see if we can find the values of the angles or the sides from this triangle there. So this is what I want to do. I want us to look at CD. We need to find that side right there. That side is the opposite side to this angle here, right? This angle at the top. Let's see if we can find some relationship between the angles and triangles so we find what is that angle there. And this is the good thing about using geometry, right? We have all these axioms that we can use. And if we break this problem apart, you will see that there are two triangles here that are similar. If you pay attention to that triangle that I am highlighting right there and the other one at the bottom, what if I tell you that those triangles are similar triangles? And the reason that I know that they are similar is because of that statement right there. Do you see how we are dividing those two triangles with that vertical line? The only way that that holds true is if those two triangles are equal, right? That is something that geometry tells us, right? If we have that configuration, this angle S that I'm calling S has to be equal to that bottom angle S. They need to be equal. Now that I know that I have those two angles and that they are equal angles, look at what I have here. I have this top triangle that has an angle of 90 degrees. So 90 degrees plus S plus something needs to be equal to 90 degrees plus S plus alpha, right? So the sum of all the internal angles of any triangle needs to be equal to 180, right? We know that this is true. The sum of all the angles, right, the first angle, the second angle, and the third angle of any triangle needs to add up to 180. The only way that these 90 degrees plus that s plus this unknown is equal to 90 degrees plus s plus alpha is if that angle right there is also alpha. Right? So that angle needs to be equal to that bottom angle right there. Now that we found out that this is alpha, now it's going to be a lot easier for us to figure out this opposite side, which is what we want, the CD. Right? So let's just go back to our problem right here. If we want to find now CD, which is this base, all right, the opposite of my triangle, the sine of alpha is equal to CD over BD. So the sine is equal to the opposite CD divided by the hypotenuse BD, right? Sine of alpha, CD over BD. And do we know what is this denominator right here? Yes, we do. If we look up there, BD is R times sine of beta, right? So R times sine of beta, this is what I get. The sine of alpha is CD over sine of beta. Since what I want to find is CD, I'm just going to do some simple algebra again and multiply R sine of beta to the left side. And that will give me the fact that CD is equal to the sine of alpha times R times the sine of the angle beta. Look at that. Sine of alpha times R. We know what this thing is, right? So if we look there on the top left, sine of alpha times R is Y, right? R sine of alpha. So Y is equal to R sine of alpha. I can replace this thing by Y. So if I look here, this is going to be, we know now that CD is going to be Y, that just came from up there, times sine of beta. And you should be getting pretty happy right now because AF, CD, we have just proven one of the first formulas that we got, right? That formula from the book of the rotation of vectors, which is that the new x prime, which was what we were looking for, is equal to x cosine of beta minus y sine of beta. We have just proven the big formula, right? Check. So this is us proving, yes, there was a lot of flex, a lot of effort, but we have just proven that this is how we find the new x prime component of this rotated vector, right? The vector after rotation. The value of the x comes from the original x times the cosine of the angle beta minus y times the sine of the angle beta. And that is a great thing, right? So this is x. We still need to go and find the y component, right? So now that we have x and that we're happy with x, what about y? So this is what I'm going to suggest. It is a lot more satisfying if you come up with the formula and the proof yourself, right? Yes, I can go ahead and start explaining all these things, breaking these things apart and find the y component, but let's propose this. I'm going to give you some time now, right? Let's just quickly pause. Try to look at this problem statement right here. Look at all these shapes, sides, vertices that we have. Look at all the vectors, the x's, the labels, and try to come up with the proof of y prime, right? This new component of the vector after rotation. I'm going to give you a couple of minutes. Take your time. I'm going to come back very soon after you're done with my proof of the y prime. So, did you manage to find the y prime and prove that it is equal to the formula that we're looking for? I'm just going to go ahead and show the step-by-step that I did, right? Hopefully it is similar to yours. So, eyes on the prize. We want to find the y component of that vector after we rotate. Right? So the y component, if you look at the graph here, the y component is BE, right? So it goes from B to E, that vertical part there. That is the y of what I want to find. So I'm just going to say that y prime is BE, right? That entire vertical side there. But again, I will have to probably break this BE apart, and I'm going to say that the entire BE is equal to BC plus CE. Right? So the top part, BC plus CE, is equal to the entire BE. So y prime equals to BCE plus the bottom part, CE. And that will be okay, but I want to go even a little bit further, right? Do you see how CE, the left side of that rectangle CE, is the same as DF? So CE is equal to this side DF, right? Since it is a rectangle, the left side is equal to the right side. I am going to not use CE, right? I'm not going to use CE, and I'm going to replace CE by DF. So DF. Again, instead of using CE, I'm going to use DF. They are equal, right? So this is what we have. We need to find BC and we need to find DF. As soon as we find BC and DF, then we can find the solution, and hopefully it's going to be the formula that we are looking for, right? The formula that I showed you, that it is the actual rotated vector formula. So let's just break this apart. Let's look at the first term, BC. This is what we want to focus now, BC. So let's just look at BC. BC right there, we can look at that BC as being the cosine of that angle alpha there. It is the adjacent over the hypotenuse. So it is BC divided by BD. BC divided by BD, exactly what we have. Let's look at what we have here. We have BD. Well, look at that. Up there, BD is r sine of beta. So I can replace this denominator by r sine of beta. Let's do that. Same thing, cosine of alpha is BC divided by r sine of beta, just replacing BD. If I come here and I just do some simple algebra, because what I want to find is BC, so let's just multiply everything by r sine of beta. It gives me that BC is equal to the cosine of alpha times r times sine of beta. And we know that we have this thing right here, cosine of alpha times r. This thing is x, right? So I can replace the entire cosine of alpha times r by x, which is that thing on the top left. There we go. We found BC. BC, that value right there, this first term right here, is equal to x times sine of beta. Great. One thing done. Let's look at the other part right here, right? So plus df. We have to look at df now. We need to find this side right here. So we probably have to look at the angle alpha there, right? So we're going to have to find, this is the opposite side to this triangle, and then we have the adjacent. Let's look at that thing. The sine of alpha, right? So the sine of alpha is going to be the opposite df divided by the hypotenuse, AD, right? The hypotenuse is AD. Look at this, beautiful AD. We have the value of AD up there is r cosine of beta. We're going to replace the denominator. You probably know where we're going with this, right? So the sine of alpha is df divided by AD, which you just saw, it is r cosine of beta. Multiplying this thing, right, just simple algebra, we want to find df. So df equals to, we multiply sine of alpha times r cosine of beta. Same thing, you probably know already, sine of alpha times r. We know what this is, right? Y on the top left of our slide, r sine of alpha times r. So this is y. And here we go. We have our second important formula. So you should be getting pretty excited by now, because we have just proven that this thing right here and this thing right here, if we add them together, right, we just proved this one, we proved this one, now we have to just join them right here to find my y prime, which is what I want to find at the end. there you go. So we have just proven that y prime, the component y of my rotated new vector, is equal to the original x times sine of beta plus y times cosine of beta. And this is the formula that we saw before on our slides, right? That is the formula that you will see in most books. That is the formula that you will find in Wikipedia. So these two right here are the formulas, right? These are the final big formulas that we have just proven, right? I know it is a lot of work, but this thing right here, many books, they just take these things for granted. They just tell you the formula and then just say, look, accept that this is true and move on with your life. I think it's a lot more satisfying if we break this problem apart, if we look at all these axioms, if we try to find this geometrical proof of why are we having this new x as x cosine of beta minus y sine of beta, and why is the new y component x sine of beta plus y cosine of beta. Correct? I think it is super important for us to understand, especially for us to increase our chops in this whole mathematics world, right? As programmers, as game programmers, as 3D programmers, as physics programmers, which is my field. It is super important for us to at least be comfortable working with these values. And I thought it was super important for us to review this thing, put things into context, and show why, if we rotate a vector by an angle beta, the new x prime and y prime come from these formulas right here. And I think that is a beautiful thing. But wait, stop, right? Just before we go. If you like this type of content, consider giving a thumbs up. And also remember that we have full-feature courses, right? At pikuma.com, you will find courses on computer graphics, on physics engines, on game programming, that we really go and we expand these mathematics ideas for computer programming, computer games. So this is something that you will find a lot in those courses, right? So if you think this is super cool, consider going at pikuma.com and checking the courses as well. Thank you very much. See you soon.